Hello, welcome back. We're going to continue our discussion of measures of variation. Let's see here. So we left off with finding the variance and standard deviation of a population and of a sample. So we had already figured out how to find it for a population, and now we just needed it for a sample. And we're just going to quickly kind of go through here. So for a sample, the key thing to look for is when you go, so you enter your data into into L1. So you enter your data into L1, and then you go to one var stats, and when you compute your one variable statistics, because we're looking for sample variance, right, with sigma squared, and sample standard deviation, you are going to use the value for Sx. So this is going to be your sample standard deviation. Okay, so we've got, again, a whole bunch of words to describe how to do it. The formula differs. Let me point this out. The formula differs here because you're dividing by n minus 1 instead of the big N. Why is the formula different for sample versus population? Just kind of it's been found, through years and years and years in the theory. They've kind of figured out that because the sample is smaller than the population, you'll get a better measure of the standard deviation if you divide by n minus 1 to compensate for the fact that the sample is smaller. Okay, so again, let the calculator do all of that heavy lifting for you. Let's see here. Practice with this example here. You should not need to do anything different in your calculator because the data entries should still be in your list L1, and the only issue should be just kind of scrolling down with your one var stats and looking at Sx instead of sigma x. Okay, so when you do that, you should see, let's make sure we get the correct answer here. So you should see that your Sx is about 3.1. So your sample variation is going to be about 9.8. Okay, and this 3.1 again corresponds to $3,100. All right. Now we're going to get to an example where you are going to use a calculator. This is finally the book is recognizing the fact that calculators and computers can be used to find the mean and the sample standard deviation. What are you going to do? You're going to enter these data entries into your list, L1. So clear your list first, enter these data entries in, and then go to one var stats. And this is what your output should be. So you can see here again the difference we were talking about with this is the sample standard deviation, whereas this sigma x here is your population standard deviation. So if your data entries are values for the entire population, you use sigma x, and if they are simply values for a sample of the population, you're going to use Sx. Okay. Now, this is kind of what I was describing from before, interpreting standard deviation. Standard deviation is a measure of the typical amount that an entry deviates from the mean. Look at this first histogram. So here, all of the numbers are 5, right? So all of the numbers are 5, like you've got just a whole bunch. You've got 8 numbers, right? So I know the set of numbers was just 5/8. 1, 2, 3, 4, 5, 6, 7, 8. How do I know that? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this value, data entry, had a frequency of 8. So if the data set consists of only integers or whole numbers, then this is our data set. And now, what is the variation? What's the deviation? There is no deviation. All of the numbers are the same, right? So standard deviation is equal to 0. And of course, the data is very, very close to the mean. In fact, it is the mean. We move over here, and we've got a little bit of a standard deviation. So standard deviation is 1.2. Still has the same mean, right? Still has the same center. Remember, the mean is a way of measuring the center. What's the center of all three of these? 5, right? So all three of these data sets have the same center, the same mean of 5, but they have different standard deviations. Some of the data is more spread out. This data is really spread out. It's very far from the mean, right? So like here, we could say that a data set would be 3 2s, 1 3, 1 7, and 1 2, 3 8s, right? And now if the mean is 5, all of these numbers are pretty far from 5 compared to this first data set over here where all of the numbers are exactly equal to the mean. Okay, so this kind of just highlights, looking at these three graphs, highlights the impact that the standard deviation can have on a data set and how two data sets are totally different if they have different standard deviations. Okay, so now let's look at the empirical rule. It's also called the 68, 95, 99.7 rule. And it essentially says that about 68% of the data is going to be within one standard deviation of the mean. Okay, and about 95% of the data is within 2 standard deviations of the mean. And 99.7% of the data is within 3 standard deviations of the mean. So now what does this mean to say that you are within 1 standard deviation of the mean? So that means that you are above or below, but at most 1 standard deviation. So you'll notice here in the middle we've got the mean, because remember we've got a symmetric distribution, and that's one of the properties of symmetric distributions, is that the mean is the same as the median, is the same as the mode, and they're all in the middle of the distribution, right? So in the middle we've got our mean, and now if we go up or down 1 standard deviation, we're saying that 68% of the data is between x bar minus s and x bar plus s, right? So that's 68% of the data. And now because this distribution is symmetric, if 68% is between here and here, that means that 34% has to be below and 34% has to be above, right? Because 68% divided by 2 is 34%. And similarly, 95% of the data is going to be in between, is going to be within 2 standard deviations of the mean. And then 99.7 is going to be within 3 standard deviations from the mean. So 99.7% is going to be within 3. So what's left over? If you are more than 3 standard deviations away from the mean, which means you're over here and all the way back over here, that is 0.03% of the data is going to be that far away from the mean. Okay, which means it's very, very rare to be that far away. Let's look at an example of how to use the empirical rule. And remember again, thank you. The empirical rule is connecting. It allows us to connect the standard deviation to the mean under certain circumstances. What has to happen? You have to have a symmetric bell-shaped distribution. So if your distribution is symmetric and bell-shaped, then this is what you know about the standard deviation. So let's look at this example here. So in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. was 64.3 inches with a sample standard deviation of 2.62. Estimate the percent of the women whose heights are between 59.06 inches and 64.3 inches. So the first thing to know is to know that heights are normally distributed. Okay, so that's kind of something that you have to bring to the table here, is that heights are normally distributed. What do I mean by normally distributed? I mean the heights are symmetric and bell-shaped. Okay, what does this mean? This means that most people are, like close to average height, and then you've got a few people that are really short and a few people that are really tall. Okay, and like very, 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 very few people are super tall, and very, 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 very people are super short. And it's, whenever you have a group of people of a certain age, right? Same thing with babies. If you measure how long babies are when they're born, you've got very few people, a few babies that are really short, and a few babies that are really long, and most of the babies are, somewhere in between. Same thing with weight. Anytime you weigh anything, if you weigh, humans, if you weigh animals, very few, animals of a certain size or of a certain age, or very few humans of a certain age are going to be very, very light, and very few humans are going to be very, very heavy, and most humans are going to be somewhere in between. So we're going to use this to say that our distribution is bell-shaped, so we can use the empirical rule. So now, what is the mean? The mean, we're told, this is for 20 to 29-year-old women, right? The sample mean height was 64.3 inches. So this means that here, this sample mean is 64.3 inches. So that means that, let's see here. We need this other piece of information with a sample standard deviation of 2.62. Okay? So S is equal to 2.62. And X bar is equal to 64.3 inches. And S is 2.62 inches. So what is this X bar plus S? X bar plus S is going to be 64.3 plus 2.62, which is going to be 66.92. Okay, so right here, 66.92 is right here. You see that? And now what is this number right here? Well, now we need X bar minus S, which is 64.3 minus 2.62. $61.68. Okay, and then what is X bar plus 2S? Is going to be 64.3 plus 2 times 2.62. It's going to be 69.54. And then what about minus? So 59.06. Okay, and I believe these are the key key numbers that were used in the question. So the question was asking what percent, estimate the percent of women whose heights are between 59.06 inches and 64.3 inches. Okay, so if we want to estimate the number that are between 59.06 and 64.3, we need to estimate what percentage falls in the purple area. Now, we've been told that 34% is in this area, is between 61.68 and 64.3. And then 13.5% is between 59.06 and 61.68. So in the purple region, we just need to add up 13.5 plus 34%. So that'll give us 0.5, and then that'll be 7. 47, so 47.5%, approximately 47.5% of women ages 20 to 29 are between 59.06 inches and 64.3 inches. Okay, so that's how we use Chebyshev's rule. And the empirical rule. Now let's look at Chebyshev's theorem. Chebyshev's theorem kind of gives us a better estimate of the empirical rule. The empirical rule only counts by full standard deviations away from the mean. Chebyshev's theorem allows us to look at k standard deviations away from the mean, where k is greater than 1. So, for instance, let's look at this. So the portion of any data set lying within 2, let's just take, for example, say k is equal to 2, right? The portion of any data set lying within 2 standard deviations of the mean is at least, now if k is equal to 2, then we'll have 1 minus 1/4, or 75%. So notice that with the empirical rule, we are saying that what lies within 2 standard deviations, the best we can say is, let me get something lighter here. The best we can say is 95% is within 2 standard deviations. However, with Chebyshev's theorem, we're able to improve on that and say, no, actually, 75% of the data lie within 2 standard deviations of the mean. Okay? Now, let me kind of explain what's going on. So with Chebyshev's theorem, we are no longer making the requirement that the data is bell-shaped. Okay? So Chebyshev gives us worse, in a sense, estimates. It gives us worse estimates because we're saying at least 75%. It could be 85%, it could be 95%, it could be 99%, we're not sure. At least this percentage of the data lies within k standard deviations. But the trade-off is that we can use this for any distribution, a distribution of any shape. So it doesn't have to be symmetric. It doesn't have to be bell-shaped. Okay? So Chebyshev's is more broad, and in some ways it's more useful because you can apply it to more data sets. Okay, so let's look at an example here. The age distribution for Florida is shown in the histogram. Okay, so now just between me and you, what is the most popular age group in Florida? It looks like the most popular age group is between 30 and 45, right? Because that age group has the highest frequency. Okay. So now let's look at this problem here. So it says we want to apply Chebyshev's theorem to the data using k equals 2. What can you conclude? Okay, so now according to Chebyshev, the portion of any data set lying within 2 standard deviations of the mean is at least, now for k equals 2, is at least 75%. So we would like to say here that at least 75% of the data set lie 75%. I don't know if that should be lies or lie. The portion lying of the, so let's just switch it to 75% of the data lie within 2 standard deviations of the mean. Okay, so now what is, first of all, I'm just going to locate the mean on the graph. So this is computed for us here. The mean is 39.2, which looks like it's about here. I don't know if you can see that. So it looks like that's the mean. Okay, so now to lie within 2 standard deviations of the mean, that means we're looking at mu plus 2 sigma and mu minus 2 sigma. These are going to be the boundaries for being within 2 standard deviations. So mu plus 2 sigma is going to be 39.2 plus 2 times, now sigma we are told is 24.8. Okay, which will give us so we want 39.2 plus 2 times 24.8, 88.8. Okay. Ooh, that's a lot. It's like maybe right here. Okay, and now what about 2 standard deviations below the mean, which would be mu minus 2 sigma. Okay, let's see here. Well, that is negative 10.4. Now, negative 10.4, do you see how that doesn't really make sense? Because how can you be negative 10.4? Should probably be here. How can you be negative 10.4 years old, right? So, within 2 standard deviations of the mean, we just stop here at 0. So we're saying anyone from age 0 all the way up to this 88.8. Okay, so let's go ahead and clean this up a little bit. So we found out, we computed, what does it mean to say that you are within 2 standard deviations of the mean for this data set based on this computation of the mean and this computation of standard deviation. Within 2 standard deviations of the mean means between 0 and 88.8. Between 0 and 88.8 years of age. And now, what does the data represent? So that's one more thing that we can kind of clarify, is we're saying at least 75% of the data. What is this data? Age distribution for Florida. So 75% of the people in Florida are between 0 and 88.8 years of age. So let's put this, of the people in Florida are less than 88.8 years of age. Okay, so then that would be how you would say it, how you would explain this kind of in English to someone, right? So this top part here, at least 75% of the data lie within 2 standard deviations of the mean. That's statistics talk. So that's stats talk. And if we just have regular day-to-day talk, we would say, oh, at least 75% of the people in Florida are less than 88.8 years of age. Okay. All right. Now the last thing that we've got 2 more points to hit here. And this one right here, which is standard deviation for groups data. This is very similar to when we calculated the mean for groups data. And what we want to do is we're going to look at this example here. We've got the formula back here. So here's the formula. You're looking at the squared deviation times the frequency. And then that divided by n minus 1. But notice that here, this x is going to be the midpoint of your class. Okay, so you're going to use here we go, by using the midpoint of each class. Okay, to estimate the class. Now, let's look at this example here. You collect a random sample of the number of children per household in a region. Find the sample mean and the sample standard deviation of the data set. So, here's what we're going to do. First of all, we want to use technology. So we're going to use that TI-84. But in order to do that, what we need to do is we need to come up with L1 and L2. So in order to use the calculator to find the mean and the standard deviation, we need to have our values for L1 and L2. So our values for L1, so here's what we can do. We've got all of these numbers here, so it looks like we could actually just write down, let's see, it looks like we've got 0, 1, 2, 3, 4, 5, and 6. So we could have here 0, 1, 2, 3, 4, 5, 6. Okay, so we don't need to have midpoints because we can just have our, because we have the actual data right here, right? We weren't given a frequency distribution, we were given a bunch of points. So we can use these bunch of points, but we can collect them so that we're not entering in all of this data one by one into L1. So for L1, we're going to have 0, 1, 2, 3, 4, 5, 6. These are the possible data entries, and then L2 is going to be the frequencies at which those data values occur. So we have to see how many zeros do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 zeros. How many ones? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, 19. How many twos? 1, 2, 3, 4, 5, 6, 7. So 7 twos. How many threes? 1, 2, 3, 4, 5, 6, 7. 7 threes. How many fours? 1, 2, 2 4s. How many 5s? 1, 1 5. How many 6s? 1, 2, 3, 4. 4 6s. Okay. So 7 7 2 1 4. 7 7 2 1 4. All right. So you enter in you got your L1. You enter in your L1. You enter in your L2. Okay. And now you go to on your calculator. I'm just going to kind of tell you how to do it. You're going to go to Stat, and then once you're in Stat, click Stat, and then arrow over to Calc, and then arrow over to 1var Stats. Okay, then you're going to hit Enter. Now you need to tell 1var Stats that what you need to do is you need to tell them that you're not going to just use list 1, but you're going to use list 1 and list 2. So click the second button, and the number 1 button, and this is to get L1. Then you want to hit a comma. So there's a comma button, and this is to get a comma. And then you want to hit second and number 2. This is to get L2. Okay. And then you want to hit second. Sorry, I already said that. Then you want to hit Enter. And that should give you your display of your one variable statistics for this grouped data. And when you scroll down, you should be able to find your SX should be about 1.7. And the units for this, the units for it is based on what the data was. So this is the number of children per household. Right, so the units are number of children. So about 1.7 children. Those are the units. Okay. All right. And lastly, I'm going to leave you to kind of look at this coefficient of variation. It is a way to allow you to compare data sets that have 2 different units. So imagine if you're comparing one data set and the units of the data set are in pounds, and another data set, the units are in dollars, right? And you want to see how which data set is more spread out. A way to do that is to look at the coefficient of variation, because it describes the standard deviation as a percentage of the mean, right? So since standard deviation and mean both have the same units, those units cancel out, and the coefficient of variation actually has no units. Okay, it's just a percentage. All right. So I said here it allows you to compare the variation in 2 data sets that have different units. It allows you essentially to compare apples to oranges. Okay, so let's look at this example here. So this is our last example. Woo, we made it. And we want to compare the heights and the weights of a basketball team. So you want to know, you have a basketball team, you want to know is there more variation in the height of the people on the team, or is there more variation in the weight of the people in the team? Okay, so the weights here are in pounds, and the heights are in inches. Okay, so here's what we're going to do. Let's go back to our formula. The coefficient of variation is the standard deviation over the mean times 100%. So first we're going to do it for the heights. So this should be really straightforward, because in your calculator, in L1, you enter these numbers here. Okay, and then you go to Stat, then go to Calc, and then go to 1var Stats, hit Enter, scroll down, and you should get you should get 3.3 for your standard deviation, and you should get 72.8 for your mean. And when you multiply that by 100%, that should be about 4.5%. Now, let's work on the coefficient of variation for weights. Okay, so here you're going to enter into another column. You can either clear L1 or you can enter it into L2. These are our weights that we're going to enter in. Okay, so these are your data values. On the right-hand side, all right, and so now here we have the same formula, sigma over mu times 100%. And if you did it correctly, remember you should be using that sigma x for your population standard deviation. It should be about 17.7 for the weights, and your mean should be 187.8 multiplied by 100%, and you should get about 9.4%. So here's how we interpret these numbers. This 9.4% is about twice as much as the 4.5%, right? So the weights are more variable than the heights. So we say the weights of the basketball team, which is about 9.4% coefficient of variation, are more variable than the heights, which had about 4.5% coefficient of variation. All right, so what did we do? We did a lot today. So we, just in summary, we've got a couple of different ways that we look at variation. The easiest and the straightforward is to look at the range. A more sophisticated way is to look at the variance and standard deviation. And then that last way, which is the average deviation from the mean, like I said, we don't really talk about it, but I just want you to be aware of it. Okay? The next thing we did was we looked at the empirical rule, which only applies for symmetric distributions. And we looked at Chebyshev's theorem, which applies for any distribution. So Chebyshev's theorem is not going to be as exact, but it does, you can use it in with more distributions. Okay, and then we looked at approximating the sample standard deviation for groups data. Use your calculator. And lastly, we looked at the coefficient of variation and how to use that to compare variation in different data sets.